Hey guys, Mathmania here. Today we're going to be taking a look at how we can add and subtract matrices, a few properties of adding matrices, and then finally we're going to tackle some pretty non-common problems of matrices, but interesting nonetheless. Alright, so let's actually discuss some theorems and prehand properties we need to know before you can add and subtract matrices. So one of these prehand properties would be that when you add or subtract matrices, first check if they have the same order. And in my previous video on matrices and determinants, I went into what this means, the same order. But if you haven't watched that, no worries. I've listed it over here. Same order of matrices just means same number of rows and same number of columns. Order, when we're talking about a matrix, the order of a matrix is going to be the number of rows, number of columns. If you want to know more about that, just go ahead and watch my previous videos. But in this case, what I mean to say is that, let's take this for example. The number of rows this has is 2 rows, and the number of columns it has is 2. Now, the number of rows this has is also 2. But the number of columns this has is just 1. So these matrices can't be added or subtracted because the number of columns differs from this matrix to this matrix. Whenever you're adding matrices, all the matrices need to have the same number of rows and the same number of columns. But over here, that is not the case. We actually can add or subtract, in this case, these two matrices. So the number of rows in this case are 2, number of columns are 3. In this case, the number of rows are 2, and the number of columns are 3. So in this case, we can subtract these matrices because the number of rows is the same, and the number of columns is also the same. So let us see how we can add these two matrices. In this case, you would just add these two, you would add these two, and you would add these two. And you would do the same thing for the bottom. You would add these two, add these two, and add these two. Now in this case, this is just going to be equal to 1 plus 6, which is 7. We have 2 plus 5, which is also 7. We have 3 plus 4, which is also 7. So what you see over here, I'm just adding these elements as I regularly would. But the thing to note over here is that this is in the first row, first column. I need to add this element with the element that's also in the first row and the first column. I'm taking this element. This is in the first row, second column. This is in the first row, second column. I need to add that with the element that's also in the first row, second column. So let's keep going. This is second row, first column. I have to add that to second row, first column, which is also 7. Here, 5 and 2, that's 7, and we have 6 and 1, that's 7. So the answer to adding this matrix and this matrix is going to be 7, 7, 7, and then 7, 7, 7. Now on to our next problem. Hopefully you kind of get the hang of this. This time we are subtracting two matrices. So once again, it's going to be the exact same process as last time. So we're going to take the element in the first row, first column. We're going to subtract that with 9, which is in the first row, first column. So in this case, we're going to take these two, we're going to take these two, we're going to take these two, and we're going to take these two. So this is 0 minus 9, which is 9. We have 3 minus 8, which is minus 5. We have 2 minus 4, which is minus 2. And we have negative 1 minus 1, which is negative 2. So now let's get into the properties, and the properties that I'm going to be discussing right now is just for adding matrices. So forget subtracting matrices for a second. Let's just focus on adding matrices. So our first property is that assume A and B are two matrices, and if you add A plus B, that's going to be equal to B plus A. And this is the commutative property. So adding matrices is commutative. And we could see that right here. We have a matrix A, 4, 3, 9, 7. We have a matrix B, 2, 1, 3, 4. And in this case, if we add what's on the left, we get 4 plus 2, which is 6. We get 3 plus 1, which is 4. And now solving the right side, we can see that both the left side and the right side are equal. So yes, adding matrices is indeed a commutative property. And one thing to note, you don't only need to have two matrices. You can have 5 matrices, and in that case, you would have something like A plus B plus C plus D plus E, but it doesn't matter which way you like put them. You could have D plus C plus B plus E plus A, and they would still be equal to each other. So just wanted to point that out. You don't only need to have two matrices. You can have as many matrices as you want. It's still going to be commutative if you add those matrices together. All right, so our second property is that now we're assuming we have three matrices, but once again, you can have as many matrices as you want. But let's say we have A, B, and C. Those are our matrices. And this theorem states that A plus B plus C is equal to A plus B plus C. And this is the associative property, meaning that it doesn't matter where we put these parentheses, the answer will still be the same. In other words, no matter what two matrices we add first, the answer is still going to be the same. So we have an example over here. Basically what this is saying, this is matrix A, this is matrix B, this is matrix C. If we solve these two first and then add C, that's going to be the same thing as solving these two first and then adding A. So pretty basic stuff. Much of this is built on our prior knowledge that we probably learned in like 3rd or 4th grade with commutative and associative properties. But now we're just applying them to matrices. Now I'm just going to go over a few more properties. And our next property is saying that matrix A plus this O is equal to O plus matrix A. Now, what is this O? This O is essentially a null matrix. And a null matrix is where every element in that matrix is just 0. So this is going to be O and this is going to be O because every element in that matrix is 0. And this is going to be A. And now this is sort of like the commutative property we saw. This is A plus O is equal to O plus A. That's commutative property. But another thing to also note, and this might be pretty obvious, is that A plus O is equal to A. This null matrix basically acts like a 0, like you're not adding anything to any of these terms. So obviously this added to this is just going to be that original matrix we had because you're just adding zeros to that. All right, so now for our fourth property, for every matrix A, there exists an inverse, and we're going to denote that by a to the power minus 1, where a plus a to the power minus 1 is equal to that null matrix. So remember, it's not 0, it's a null matrix. And in this case, I have an example for you. If A is this matrix right over here, 2 rows, 2 columns, then the inverse of that will be this. And that is because if you add these two matrices together, you will get a null matrix. And these two matrices are related. So this was the original matrix, and this is the inverse of that matrix. Because if you do 4 minus 4, you get 0. You do 3 minus 3, you get 0, and so on and so forth. So once again, to recap, you have a matrix, and you add the inverse of that matrix to it, you're going to get a null matrix. And now on to another property, we're going to be multiplying by a scalar. So here's an example. Scalar just means a value. So this is going to be our scalar, which is 3, and this is our matrix. And multiplying a matrix by a scalar is pretty simple. You just multiply this scalar by every element in that matrix. So you have 3 times negative 7, that's negative 21. You have 3 times 0, that's just 0. 3 times 8, that's 24, and 3 times 2, that is 6. So that's pretty much all you need to know for scalars being multiplied by matrices. Another example would be right over here. If A is a matrix that's defined by 14, 6, 27, and 2, then minus A is the same thing as minus 1 times this matrix A. So then we just multiply this by minus 1. So now we have minus 1 times 14, which is minus 14, minus 1 times 6, which is minus 6, and so on and so forth. So now we have this question, and this is a little bit harder than the two questions we did previously where we just added and subtracted numbers. We're actually bringing in trigonometry to the mix, and now we're multiplying by a scalar, and we're adding. So this is a two-step problem. First, we need to address the scalars, and then we need to address the adding part. So let's get right to it. When you always see this matrix problem first, let's always distribute the scalars. That's what you should always do. And that makes perfect sense. We always know we have to multiply or divide before adding and subtracting, and multiplying by a scalar is multiplying. So we have to multiply first, and then we're going to add. In this case, let us multiply this So let's pick this one. So we have cos theta times cos theta, that's cos squared theta. Cos theta times sine theta, that's cos theta sine theta. Cos theta times minus sine theta, minus cos theta sine theta. And cos theta times cos theta, that's cos squared theta. And notice when I multiply by the scalar, the order stays the same. So multiplying by the scalar does not change the number of rows or the number of columns. Just wanted to point that out. Plus sine theta times sine theta, that's sine squared theta. Sine theta times minus cos theta, that's minus sine theta, cos theta, a lot of trigonometry. Now that we have multiplied, we can add everything together. So we have cos squared theta plus sine squared theta. Well, we know our trigonometric formulas, right? So we know cos squared theta plus sine squared theta is just 1. We know cos theta sine theta minus sine theta cos theta, that's just 0. So we can put 0 there. And we have minus cos theta sine theta plus sine theta cos theta, that's also 0. And finally, we have cos squared theta plus sine squared theta, and we know our trigonometric identity, so that's 1. So here we have another question, a little bit tricky. We have x plus y is equal to this matrix, okay, and we have x minus y is equal to this matrix. Find x and y. So if you want, please feel free to pause this video and give this problem a go. So let's dive into the solution. What I see right off the bat is that I see this positive y and this negative y. So I think if I add these two, I can cancel that variable out, and that's exactly what we want. So I'm going to have x plus y plus x minus y, and that is equal to this matrix right over here being added to this matrix right over there. So 3, 0, 0, 3. Left side, these two get canceled. Great, we eliminated one variable. We're left with 2x is equal to, and since we know how to add matrices, we have 7 plus 3, 10, 0, 2, 8. Now we have to divide both sides by 2 because we just want the x. Dividing both sides by 2 is the same thing as multiplying both sides by 1/2. So we're left with x on the left side, and now we have 1/2, 10, 0, 2, 8. And I just brought this 1/2 to the front because that's usually the convention we use. And now this is a matter of simply expanding and simplifying. So 1/2 times 10, that's 5. This would be 0, this would be 2, and this would be 4. And this is our value of x. But now we also have to find the value of y. So once again, like a regular system of equations, you can plug it into this equation or this equation. Let's plug it into, let me actually plug into this equation because this looks a bit easier. Let me label that this equation. So now let me erase most of this. So this is our value of x. Let us replace that. So we are left with 5, 0, 1, 4 plus y is equal to 7, 0, 2, 5. Then we want to isolate y. Oh, there we go. We want to isolate y, so let's take that to this side. If we take a matrix to the other side, the sign switches. So on the other side, it would look something like this. And you can see how basic algebra laws can also be applied to matrices. Now, since we know how to subtract matrices, this would just be 7 minus 5, which is 2, 0 minus 0, which is 0, 1, 1, and that is the value of y. So this is going to be our last problem. We have find x, y, z, and t if 2 times this matrix plus 3 times this matrix is equal to 3 times this matrix. In this case, I think it's best to actually expand everything. Let's try expanding everything. 2x, 2z, 2y, 2t. And that's because I just expanded 2 to each one of those elements, hence multiplying by a scalar. Plus 3, negative 3, 0, 6. Same thing, 3 times that, same thing for the 2 elements at the bottom, is equal to 3 times 3, which is 9, 3 times 5, 15, 12, and 18. Left side, I see we can add these two matrices, so let's go ahead and do that. We're left with 2x plus 3, 2z minus 3, 2y plus 0. So I'm just going to leave it as 2y. And then 2t plus 6. And we can't simplify the right side, so let's say 9, 15, 12, 18. I just kept that the same. Now we actually have 4 equations for variables, so we can find each one of those variables pretty simple. And that is because let's take this and this. These two terms have to be equal. This is because this has 2 rows and 2 columns, and this also has 2 rows and 2 columns. This means that the element in row 1, column 1, has to be equal to this element in row 1, column 1. This element over here in row 1, column 2 has to be equal to this element over here in row 1, column 2. So let's actually do that. We have 2x plus 3 equals 9. We have 2z minus 3 equals 15. We have 2y is equal to 12, so 2y is equal to 12. And then we have 2t plus 6 is equal to 18. 2t plus 6 is equal to 18. And solving these equations, we get these values of x, y, z, and t.